Good evening, class. Just wanted to say hello and welcome you to this video. This is lesson 3.3, and tonight we're going to be talking about the greatest common factor. And we're going to start this lesson right here on this screen, because everything that we need to know about what this lesson involves is in these three words. These three words are very powerful. So we're going to actually work backwards. All right. What's going to happen is I'm going to give you two numbers. Let's just take, for instance, 24 and 32. Let's say those are my two numbers. Okay. When I ask for the greatest common factor, I'm always going to give you two numbers, and I'm going to say what is the greatest common factor of these two numbers. And actually, we'll have a few examples later on where maybe we'll start with three numbers. But what I'm asking is every one of these words is really loaded. Okay. First of all, what does it mean to be a factor of either of these numbers? Well, let's think about our definition from last night's lesson. A factor, if you recall, think about it, is a number, a whole number, that divides another whole number evenly. Okay? So if I'm looking for a factor, I'm looking for a number that divides these numbers. Okay? The fact that I'm looking for a common factor means I'm looking for a number that divides both of them. So in other words, it's a number that divides each of the numbers that they have in common. So we're looking for a common factor. I'm looking for a number like 1 that divides 24 and divides 32. Okay? But I'm not just looking for any common factor. Let's throw in the last word. I'm looking for the greatest such number, the biggest number that divides both 24 and 32. So when I say greatest common factor, those are really loaded words. I'm looking for the biggest number that is a factor of both numbers. Okay? Alright, so that's what we're trying to do. So now let's look at some ways to do it. Okay? So let's take those numbers again, 24 and 32. Let's go to a new screen, 24 and 32. And the question will say, usually find the greatest common factor, or it might just say find the GCF, which is just a short acronym for greatest common factor. Okay, well, one way we can find the greatest common factor of these two numbers is I could literally take both of the numbers, just like we did yesterday in classwork, and write out all the factors that each of the numbers have. So for 24, we'd have 1 and 24. We'd have 2 and 12. We'd have 3 and 8. And we'd have 4 and 6. Oops. Okay. And for 32, we write out all its factors. We'd have 1 and 32. We'd have 2 and 16. 3 does not go into 32, but 4 does. So we'll have 4 and 8. And let's see, 5 doesn't go in, 6 doesn't go in. I think that's it. So we got a big space in the middle. All right. So now let's look through the numbers, and let's look for the biggest number they have in common. In fact, actually, let's look for all the numbers they have in common. Let's see, they both have a 1, so there's a common factor. But it's not the biggest one because they also both have a 2. And that's still not the biggest factor because they also both have a 4. And finally, they both have an 8. So I'll circle these. Okay. If I look any bigger than 8, the 24 has a 12 and a 24, but the 32 does not. And the 32 has a 16 and a 32, but neither of those divide 24. So for this example, the GCF of 24 and 32 is equal to 8. It's the biggest number that was a common factor of both numbers. All right. Now you might think, okay, that's all you need to know. You know what greatest common factor is. You can always write out these lists of factors and you can find the biggest number. All right. So you probably think, all right, that's it. That's all I need to know. I'm good to go. The problem is, what if the numbers aren't small like 24 and 32? What if you have huge numbers, things like 24,800? and 15,600, and you're looking for the biggest number? Think about how long it would take you to write out all of the factors of a number like 24,800. You could be doing that. That could take your whole class period of classwork. Okay, so it's probably good. While this method will work fine for small, and it's really a good method to kind of show you what's happening, this is not the main method that we're going to use to find greatest common factor. So you should know about this method, and if you see really easy numbers, this isn't the worst way to do it. for small numbers, but this is not the way. Okay, so listing out all the factors and looking for the biggest number in both lists is not the way I would recommend finding the GCF. Okay, so let's go ahead and let's learn another way to find the GCF, and just for comparison's sake, I'm going to use the same two numbers. So let's go to a new screen, and again, let's use 24 and 32, and the actual question would say find, let's do this in blue, same as before. The actual question would say find the GCF of 24, hold on, I don't think I've got the right number there. Yep, 24 and 32. Okay? Alright, my favorite way is called using a division ladder. Okay? And for those of you that really like to do partial quotients dividing, and I won't let you do it anymore, well, actually you're going to like this because it's a little like partial quotients dividing. So what we're going to do is we're going to write down both of the numbers. Okay, and by ladder, what I mean is you're going to make, really it's just half of a ladder. What we're going to do is we're going to draw the left little bar and a line underneath these. And I want you to look for a number that goes into both 24 and 32. Alright, so 1 goes in, but that doesn't really help us any because if you divide 1 out, you still have 24 and 32. But they're both even numbers. So probably the most obvious number to take out would be a 2. And sure enough, if I divide each of these numbers by 2, 24 divided by 2 gives me 12. Just take half of it. And 32 divided by 2, a little bit harder, but if you take half, you're going to see it's 16. And now continue the division ladder. And again, it's really only a half ladder, but let's go ahead and put it in. Okay? And put another little bracket to the side, to the left side and underneath. And now let's look for another number that goes into both of these. Okay? Well, it turns out that they're still both even, so let's take out another 2. All right? And now if I take half of 12, I get 6, and if I take half of 16, I get 8. Well, now wait a second. They are still both even, so let's do it one more time. Let's take another 2 out, and now I'm left with 3, and I'm left with 4. And if I look at 3 and 4, these can't be broken down anymore. 3 is prime. 4 is not prime, but it doesn't have any common factors with 3 other than 1, so we're pretty much done. Okay? There's actually a name for these. They're called relatively prime because they don't have any common factors. Relatively prime. And that's kind of a cool vocabulary word. I'm sorry I wrote that so sloppy. But it is relatively prime. Just like the word relative, like your mom or your aunt or your grandmother. Okay, one more time. Relative. Okay, and then ly. Relatively prime. All right? And now what I do to finish this problem up is come over here, take all the numbers that you took out, and unlike partial quotients division where you would add them all up, what we're going to do is we're going to multiply these together. So start at the top. 2 times 2 is 4, times 2 is 8. And so 8 is the GCF of 24 and 32. Now that may look like a lot more work than what we did on the front page when we did all of the factors, but in reality it's not, and especially for big numbers, the division ladder will go very quickly. Okay? And later on we're going to use the division ladder again for another key concept when we talk about least common multiple. So this is by far Mr. Gunn's favorite method. Okay, this is the one I'm really, really happy about, and the one I would strongly recommend that you really look over and really try. Okay, and we'll give you a chance to try your skills out in just a minute. But there is a third way. Okay, so list all the factors out and just look for the biggest number in both lists. That seems simple, but it takes an awful lot of work. The division ladders probably seems like a lot of work, but actually it's usually the simplest way. But there is one more way, and the last way, again, let's find the GCF of 24 and 32. And this time what we're going to do is we're going to use factor trees. Okay, so just like we did again from last night's lesson, let's take each of the numbers and let's do a factor tree. One for 24 and one for 32. Alright, so let's break down 24. There's lots of ways you could have done this. You could have broken it into 2 times 12, 3 times 8, 4 times 6. I'm going to go for 4 times 6. Because I like my trees to be balanced, and whenever I pick two numbers that are close together like 4 and 6 are, it makes my tree be a little bit shorter. Okay, 4 is not prime yet, so we're going to break it down into 2 times 2. They're both prime, so I'm going to circle them. and the 6 breaks down into 2 times 3. Again, those are prime numbers, so I'm going to circle those. Okay. Now I haven't actually found the prime factorization, so let's write that down below. We have 3 2's, so that's 2 to the third power times 3. Alright, now let's come over here to 32, and let's go over it. We'll do this one in red. So let's break 32 down. Again, let's try to pick numbers that are reasonably close together. So I'm going to go for 4 and 8. I could have started with 2 and 16. I like 4 and 8 though, because again, the 4 is going to immediately break down into 2 times 2, just like I did before. The 8 is going to break down into 2 times 4. The 2 I can circle because it's prime, and the 4, not quite done yet. We'll break it down into 2 times 2, and now I'm done. Okay, and again, it's not that weird a tree. And this is an interesting tree because 32 is actually 2 times 2 times 2 times 2 times 2, or a much better way to write that is 2 to the 5th power. Okay, again, you don't have to write the powers like this. This one really could have been, the prime factorization could have been 2 times 2 times 3. But you can see how much shorter and slicker that notation is. And by the same token, this one over here could have been 2 times 2 times 2 times 2 times 2, and you can already see how tedious that is. I much prefer writing it as 2 to the 5th. Alright, well that's all well and good, but how does that tell you what the GCF is? Well, for the GCF, what you need to do now is you have to look through the prime factorizations, and you have to look for any numbers that they both have in common. Now, as much as I like the exponent ways to write these out, actually it's a little easier when you look down below when they're all written out separately. What do they have in common? Well, both numbers have a 2. So let's include that in the GCF. We'll put a 2 there. Well, let's look again. They both have another 2. Alright, well let's put that in the GCF. We're going to multiply these again. Alright, and I can see that I can obviously do this one more time. They still have a third 2. Okay? And so we'll put that in the GCF. Now, do they have any other common factors? Well, the left one has a 3, but the right one doesn't have any 3's. And the right one, 2 to the 5th, has 2 more 2's, but we're all out of 2's in the first one. So what do they have in common? They have 3 2's. And what is 2 times 2 times 2? Well, once again, it equals 8. Alright? If you think about it, a lot of what we just did in this example is very similar to what we just did in the division ladder. These 2's right here were the same 2's that we ended up finding here, here, and here. The 2's that they had in common. Okay? And so that's the third method of finding the GCF. And this would be finding the GCF using factor trees and prime factorization. Okay? I want to continue this skill one more time. Suppose I don't do all of the, let's say I already give you the problems and the prime factorization's already done. So suppose I give you 2 to the third power times 3 to the 5th power times 5 to the 2nd power. And that's one number. And I can multiply that all together and see what that equals, but I don't need to. And let's suppose another number was 2 to the 4th power times 3 to the 2nd power times 5 to the 3rd power. Alright, I want you to look at the top and bottom numbers. What do they have in common? Well, without even really looking really closely, you can see that they both have 2's, they both have 3's, and they both have 5's, correct? Okay. Now, here's what you're really doing on the previous example. Once you have the prime factors all written out, what you're looking for is how many factors do they have in common? Well, if they both have 2's, basically, how many do they have in common? Well, if one has 3 and one has 4, well, it's going to be the smaller power. So they both have at least 3 2's. Okay? Now the bottom number has an extra 2, but the top one doesn't. So what do they have in common? They have 3 2's in common, which we know really is 2 to the 3rd power. 2 times 2 times 2, that's going to be 8. All right, what about the 3's? Well, one of them has 5 3's, 3 to the 5th power. One of them has 2 3's. Again, we're going to go with the minimum power. So this time, it's going to be determined by the bottom. The only thing they have in common is 2 3's. Yeah, sure, the top number has extra 3's, but the bottom does not. And finally, for the 5's, once again, how many do they have in common? Well, the top one has 2, and the bottom one has 3. So in this case, there's going to be 2 in common. Now, if I multiply this number out, 2 to the 3rd power times 3 to the 2nd power times 5 to the 2nd power, I will get the GCF. That is a little more complicated than what we were really doing here with this example with the prime factorizations. Okay, so what you're going to do is you're going to look for factors that are in both numbers, and you're going to look for the minimum power, the minimum exponent. Okay, just for interest's sake, 2 to the third is 8. Okay, 3 to the second power is 9, and 5 squared is 25. Okay, and without using a calculator, if I multiply these together, I'm going to use the commutative property and multiply 8 times 25 first, because that comes out a nice, neat 200. 8 quarters is $2, and then if I multiply by 9, that's going to equal 1,800. So 1,800 is the GCF. So that kind of shows you just how big those two numbers were. The top number, by the way, you might be interested to see. Like I was saying, sorry, you might be interested to know what these numbers are actually equal to. It turns out that the top number is actually equal to 48,600. And the bottom number is equal to 18,000. And so what we were looking for with these two numbers is what number is the biggest common factor, the greatest common factor, in other words, the biggest number that divides evenly into both of them. And so what we discovered was that 1,800 is the number that divides into both of these numbers. And it's the biggest number that will do that. That is what the GCF is. Okay. Now again, when you're confronted with a problem, even this one that I just gave you with these big, huge numbers, I would still recommend, for the most part, that you use division ladders. The only exceptions would be if the numbers are really small and you really want to do one, or it actually tells you in the directions that you have to do it by listing all the factors, then obviously follow the directions. Also, if you have one like this page where they've already given you the prime factorizations, then it is actually easier just to look through the prime factorizations and decide what they are. So this is going to take some practice. Don't feel bad if this doesn't feel 100% solid. We're going to practice it in class. But this video is starting to run a little bit long, so we're going to sign off for now. And the classwork tomorrow, we're going to go through these three methods, and we're going to practice finding the GCF of two numbers, the greatest common factor. Okay? Before we completely end the night, I do have a fun picture that I wanted to share with you. It turns out that the gnomes all got together, and they took this neat picture of a birthday cake. So this is my birthday cake from all my gnomes. So it's all of the gnomes signing off and saying thanks for watching, and see you in class tomorrow. Good night, everybody.